Okay, so we're kind of picking up with vectors, 2, 11, 11, 2, 15. And we know that vectors are components of motion. A vector quantity is something that has both, what? Both? Direction and magnitude, right. So 10 meters per second east, 7 meters per second south, 10 meters north. Those are vector quantities. When we solve for overall resultant displacement or overall resultant velocity or resultant anything, we have to somehow mathematically combine those vectors. But there's one other way we can combine those vectors, and that's to do what's called a graphical solution. So a graphical solution, graph means what? To write, to draw. A graphical solution is when you're actually drawing out the vectors. You're creating a careful scale, and you're measuring, and you're not doing any math. There is zero math involved in a graphical solution. So you are selecting a scale, drawing your lines in, and very, very carefully, of course I did these colors backwards, I usually do the resultant in red, connecting them with a resultant vector, and that resultant vector, when measured, will give you the magnitude of the resultant. And when you measure this with a protractor, it will give you the heading of the resultant. Because of course, the resultant has to also have a magnitude and a direction. And in terms of our resultants, these are typically not going to be just east, north, south, etc. They're going to be, 27.2 degrees north of west, 23.4 degrees south of east. Okay? Okay, so let's choose a few to do graphical solves on. This is where we actually do have to step away from the 21st century into the 20th. Protractors are in that middle space right down there, little purple bin, center near the bottom. Grab yourself a protractor, grab yourself a ruler, and we're going to start doing some graphical solves. So again, when we're doing a graphical solve, the keys are being really careful with where your line starts and ends, measuring angles well. Let's talk about those heading angles. So the problem we just had, an airplane or a roller coaster travels along for 85 meters, then turns 30 degrees above the horizon, and continues for 45 meters. We had our resultant all drawn in, and using a graphical solve, we come up somewhere in the neighborhood of 125 at, and I'm even going to say like approximately 10 above the horizon. I'll use your numbers, that's fine. That final answer for the resultant would be 125 meters at 10 degrees above the horizon. So let's talk about some of the possible headings we can have. And in the video I started to talk a little bit about east of north, south of west, all that stuff. But this other one, above the horizon, below the horizontal, out from the wall, all of these things are situational. So in each case where you're developing a heading, you have to really read the problem. Again, draw the situation. Did I mention that you should always draw the situation? You should probably draw it. That becomes more and more important as we go. Looking at the situation will give you the heading. So let me give you a really terrible example. Trying to think. Okay, let's do this. We have a little wall. Perhaps this is some sort of lake or pond with a little dock wall. And we have some sort of small creature which is capable, this is some sort of amalgamated creature with properties of multiple species, We don't know what it is. Is it a frog? Is it a bird? Is it a fish? We really have no idea. But it's capable of making really weird turns in midair. This is awful, I know. So this thing goes out and then nearly straight. Well, let's not even do that to you yet. I won't show you how ugly that can get yet. So it comes off the wall at, we'll say 25 degrees below the horizontal, and goes, I'm going to make this really easy, 10 meters, and then goes straight down into the water. We're not going to do this graphically. We don't have, well, I could have you do it graphically. I can't do it graphically on the iPad. And we don't have the tools yet to solve this kind mathematically. Yeah, sure, let's say this is a 7-meter plunge straight down. So the question is, when you do get your resultant, how will you describe that heading? So, I mean, we know, we can draw in the resultant. The resultant displacement of this weird griffin-like creature's motion, we can draw. How do you describe the heading? Okay, down and out, haha, like falling down and throwing up. There are multiple ways to describe it. You should always be referencing something in the situation. So in this case, you have two really obvious ones that you can use as references. Remember that the direction of motion is that way, okay? So what are the two obvious physical things? If you kind of look at this as a triangle, what are the two obvious things that form sides of that triangle that you can use to reference your motion? The wall and the water. Those are two things that are right there that you can use as references for your motion. Now, do we have any idea if this thing is facing north, south, east, or west? No clue. If there is no north, south, east, or west in that problem, you better not have north, south, east, or west in your headings, because you don't know. If the problem says above the horizon, below the horizon, you should be using those things in your heading. This is one of the areas, I spend more time on this than I used to, because this is one of the areas that used to really trip students up. So it's I'm red flagging that this is something that people tend to struggle with. And maybe you guys will cruise through. You guys so far are cruising through on lots of stuff, happily. So, okay, we could use the wall or we could use the water. Now, I'm not going to do a graphical solve on this. Like I said, I don't have the tools to do it on here. Let's imagine that that angle comes out to be 38 degrees. Okay. I could say 38 degrees out from the wall. I could use the wall, 38 degrees out from the wall. The other thing that is always available to me is the horizon line, the horizon of the planet. So, the horizon is not just where the sky and the earth meet. It ends up being sort of an imaginary constant in everything we do. And so we can describe that as, let me pick some other color for the horizon. We'll do green. We can describe that as 38 degrees out from the wall. We can also describe that as the complement below the horizon. And very often, if something is moving downward, there's a problem somewhere in this chapter or the next where Superman is diving off a building, So because that motion is downward, I think the key gives the answer as so many degrees below the horizon. We sometimes see below the horizontal. You could describe the motion with regards to the water. Here's the one problem you have with that. If you decide to describe this angle and use a relationship to the water, you're describing this angle, which means you're describing motion going this direction. So in order to use the water as your reference point, you really need to use this angle, and that gets really tough. So you're always better to use, let me get rid of some of that extraneous stuff. You're always better, you need to use an angle that relates back to the start of that resultant vector, okay? So that's just a little tip, trick thing. Assigned, in addition to what I already assigned, and I'll get these up on the board, page 87, number 3, number 4. Okay. Okay, and for number 91, I'll let you check answers at the end here. So what we've done so far is we've done all perpendiculars, all right angle vectors, and we've done finding the resultant. So we have been finding, oops, I should have made those different colors. Finding the resultant displacement, finding the resultant velocity. Here's an important thing, and I don't know that it's, I've said enough about it. You can do this for velocity, you can do this for acceleration, you can do this for displacement. We'll pick it up tomorrow.